Hello and welcome people. Let's have a look at this question from 2005 GATE exam. It's for 2 marks. The statement says, consider the following data path of a CPU. The ALU, the bus and all the registers in the path are of identical size. All operations including incrementation of PC and the GPRs are to be carried out in ALU. 2 clock cycles are needed for a memory read operation. The first one for loading address in MAR and the next one for loading data from the memory bus into the MDR. The instruction add R0, R1 has the register transfer interpretation of R0 gets the value of R0 plus R1. The minimum number of clock cycles needed for execution cycle of this instruction is. Then you have some options. Okay, let's solve this one. Now before watching this video, I'll recommend you to watch GATE 2005 question, GATE 2001 question and 2020 question. Okay, all these are similar questions. Now here you are given this code. We need to find how many cycles will this instruction take. Okay, so for this instruction or for this add operation, both the operands need to be in these buffer registers, buffer register S and buffer register T. That means first step is going to be copy the value of R0 as well as R1 into S and T. This is going to take 2 cycles. That means T0 and T1 will be T0 and T1 will be copying values of R0 and R1 into S and T because that's the only way to provide input to the ALU. Okay, this is ALU. These are general purpose registers. This is program counter, memory data register, memory address register, and the instruction register. So after the values are available in these 2 registers, we can then add those values. Okay, so the answer to this question is 3 clock cycles. Now, if you want to see what control signals are going to be generated for doing these things or for performing these operations, let's see those control signals as well. So here R0 is the source. That means R0 is supplying some value. That means R0 will give a out, or R0 needs a out signal. S is the destination. That means S needs an input signal. Okay. Similarly, R1 will be out, T will be in. And a simply add signal will be generated for the ALU. You can just name it signal add. And R0 here is the source. Okay. The destination. So R0 will get a signal of in. I think we must write S and T here. Yeah. Okay. So if you cannot understand this part, these are the control signals. That means we will give a out signal to the register R0. Whenever this clock cycle starts, our control unit, that is the CU or timing and control unit, will generate a out signal that will reach R0, as a result of which R0 is going to output its value on the bus. That means R0 from here will be directly connected to the bus for outputting its value. Okay. Similarly, on this clock cycle only, rather in this clock cycle only, S will be ready for accepting any value from the bus. Okay. Yeah, so the answer is 3. I'll read out the B part. This is a 4 marks question, 2 marks for each part. Okay, we'll read out the next part. Instruction call rn comma sub is a 2-word instruction assuming that PC is incremented during the fetch cycle of first word of instruction. Its register transfer interpretation is rn is loaded with PC plus 1 and PC is loaded with memory at location PC. The minimum number of clock cycles needed during the execution cycle of instruction is. Okay, so this is the instruction that we are given in the question and this is how it's interpreted. Now I'll recommend you that you try to understand what's happening and what this instruction is doing. Okay, so let's continue. This is a call instruction and this Rn is one of the general purpose registers. That means some register from these registers. And this is a memory address. Okay. Moreover, it's given this one is a 2-word instruction. That means the first word of instruction is this and this memory address takes one more word. Okay. So in total 2 words. Now, they mentioned that after fetching this part, PC was automatically incremented. That means here, when we fetched the instruction, the first step towards executing this instruction was fetching the half or fetching the first word of this instruction. Say it's here. Now, after fetching it, PC was automatically incremented. That is what was given in the question. That means initially PC was pointing to this and we fetched call Rn. That means this line. Now call Rn is fetched and PC was automatically incremented. That means PC now points to the second word of this instruction, which is this part. Okay. Now what we are doing is we are incrementing PC again and saving its value into some register. Then we are actually not incrementing PC, we are saving value. We are only saving the value PC plus 1. PC's value remains unaffected. But in Rn, the value saved is PC plus 1. Okay, so next step is we are fetching whatever data is contained on location pointed by PC into PC itself. So now I'll explain what is happening. So first of all, this is a call instruction. It may implement some function calls, etc. Okay, that means we need to save the return address. For example, while executing, here you encountered a call instruction. Whenever you will jump here after executing that function, you need to come back here also to the line immediately next to this call. That means the next address must be saved. So after you have fetched this part, PC was pointing here. That means this is one instruction in these 2 lines. The return address that has to be saved must be of next instruction. That means this one. Okay. Now PC is pointing here. We need to save this address, which means PC plus 1 must be saved into this register mentioned here. Okay. So till now what has happened? We have just saved the return address into some general purpose register. Okay. It may even be a special purpose register, but that doesn't matter. Anyways, let's see what's happening in next line. Okay. So after returning or saving the return address, we need to jump. Okay. Where do we need to jump? To this sub. Now you notice we haven't yet fetched this part. PC is pointing here, but the only thing that we have done till now is saving the return address. So we actually need to fetch this part also, then only we'll get to know the address. Okay, so whatever PC points to, we are loading that, we are kind of reading that address. Okay, that means we want to read this address sub, and where do we want to save it after reading? Into PC itself. Why into PC? Because we want to jump to this address. No, because PC always contains the address of next instruction that is to be fetched. Now, if we manipulate PC's value such that we save this value only, that means whatever address is contained in this location, we save its value into PC only. Obviously, now PC will be fetching the instruction at this address. Okay, that means we have successfully performed a jump. Okay, now let's see how will this be implemented. Okay, like what will be happening in different clock cycles. So first thing is we want to increment the value of PC, and also it's mentioned in the question that incrementing must be done in ALU itself. So these registers, this PC cannot be incremented locally. So in the first clock cycle, we are going to get the value from PC into a temporary buffer. That means PC's value is loaded into the first operand of ALU. Then we increment this operand, or we increment the value in PC using the ALU. Okay, that's given in the question that PC cannot be incremented locally. That means it needs to be incremented with the help of ALU. This value we save it in a register Rn. Okay, this is also given in the question. The value, incremented value needs to be saved into a register Rn. So the next line says M of PC is saved into PC. That means we need to access the memory, and whenever we need to access the memory, address must be present here. That means memory address register must contain the address. We cannot directly access the memory. That means step 1 for accessing the memory must be saving value of PC into memory address register. Okay, now PC's value is saved here. That means memory can be accessed at this location PC. Okay, then we need to read from memory at this location. That means, and mind it, whenever the MDR register and MAR registers are given in question, whatever value we read from memory is always brought into this register MDR. That means memory supplies a value from this address pointed by PC, which gets saved into the memory data register. Okay, so this one is the fourth clock cycle. Now, whatever we have read must be saved into PC. This value we have just read, this must be saved into PC. That means the fifth clock cycle will be MDR's value is copied into the program counter. Okay, I hope it's visible. Yeah, it is. Now, can we do something better? We don't want to spend 5 clock cycles. Can it be done? Yes, obviously it can be, but for that you need to know some basics. So first thing is, these two registers MDR and MAR are directly connected to the memory. Okay, say this is your memory, RAM or primary memory. Okay, this bus is called the address bus. This bus is called the data bus. There's one more bus that I'm not representing here. It's the control bus. Okay, anyways, let's not draw this control bus here. Now, why am I telling you these two things? It's because this bus is called the internal bus. internal bus is used for movement of data within the CPU. That means this bus can move data between ALU and some registers, or PC and memory address register, and memory data register or instruction register. Now I think you're getting the point. But this bus, this data bus, it's also called system bus sometimes. System bus has three parts: data bus, address bus, control bus. And this system bus is used for moving data from memory to CPU. Okay, that means these are two different buses. Two different buses means we can use them at same time. Okay, say you want to move data from PC to MAR, then this bus is going to be used. And at the same time you want to fetch data. Okay, let's not change MAR. Say you want to move data from some register to this temporary buffer S. That means you are going to use this bus, which is the internal bus, and at the same time you want to fetch something from the memory. That is data bus. Okay, so because two different buses are being used, you can perform these two operations within same clock cycle. Okay, the point is within same clock cycles. Now let's try to reduce the number of clock cycles here in the light of these two concepts. Okay. Now the value of PC is being copied into S. Okay. That means PC gets a out signal. Here we provide it out signal. It outputs its value on the internal bus. That means every register can see the value of PC, but the only register that will copy its value is S, because control unit is going to generate a read signal only for S. That means at this time bus has the value of PC. Possibly all registers can load that value, but only the one who gets a read signal will load it. That means we can very easily combine this as well as this instruction, because PC has anyways the same value, means S is going to contain the same value as MAR. Okay. For that purpose, what we are going to do is we'll combine these two instructions into PC MAR comma S. That means PC's value is loaded into both MAR and S. Is this possible? First of all, yeah, it's possible, because internal bus contains the value from PC, because PC is given an output signal, PC out, and both of these can be given a read signal or in signal at the same time. So both of them will load the value from bus, whatever value is on bus. Okay. Next you see, this is a ALU operation, and it's also using the internal bus, because ALU's output is saved into general purpose registers. So this instruction number 1 uses internal bus. We can do memory read at the same time, because memory read is going to need the data bus. Okay, so what you do is you combine instruction number 1 and instruction number 3, because this needs internal bus, this needs the system bus. That means this is our first instruction. Okay, first instruction is this, or first, I'll say first clock cycle. This is what happens in clock cycle 1. Let's see what happens in clock cycle 2. We'll increment S and save it into R0. As well as we'll read from the memory. Okay. Now you need not mention the address explicitly, like what memory address is being read, because it's implied by the value contained in this memory address register. Whatever value is saved in this register will be used as an address. Okay, we have already loaded this value appropriately. Anyways, So these four steps are done. T0, T1, T2, T3 are taken care of. Only remaining operation is copying the value into PC. That means third clock cycle will be this value of MDR will be copied into PC. Okay. So these two instructions, I'll not call them an instruction because this is an instruction. These are the steps for carrying out that instruction, can be translated into these control signals. Okay. Well, I have not actually written the control signals. Okay, let's write the control signals also. The control signals will be PC gets out. In the first clock cycle, PC gets a out signal. Both memory address register and S gets in signal. Then we provide a add signal to ALU and R0 gets in signal. So this is ALU increment signal. Okay. Which value is going to be incremented? Obviously, when we mean increment or when we say increment, the first operand is going to be used as the input value. Increment instruction needs only one operand. The first buffer is going to provide that value. And next one is memory is going to supply a value. So we read from memory. And this is a M read. Okay. And MDR is going to load that value. That means MDR will get a in signal. Similarly, in third one, MDR will be given a out signal. PC will get a in signal. Okay. So this is the translation into control signals. That means in total 1, 2, 3. 3 clock cycles are used here. So answer to both of these questions is 3, 3. Okay. I'll see you in the next video.